A very quick word about myself. My name is Chen. I'm in the core developer team for COMPAS since 2019. I've been a board member at the COMPAS Association, and recently, and very proudly, like I just said, I finished my PhD at a blog research group on the topic of data models for AEC and their AI integrations, and with 1/3 of my research focused on the topic of BEAM and IFC. And for today's update about COMPAS IFC, I would like to answer these three questions. Why should you use IFC? Why should you use COMPAS IFC? And why should your AI use COMPAS IFC as well? So why IFC? IFC, or the Industry Foundation Classes, is the international standard for the building information modeling. It's a neutral format that is supported by almost all major BIM platforms, and it is increasingly mandated by the governments around the world as a compulsory type of project delivery mechanism. And this means that if you are a practitioner, it is a reality you can have to deal with every day, especially if you're doing large and complex international projects. And if you're a researcher, it's perhaps one of the best vehicles for you to plug in your innovative products or process into this widely accepted industry format. Well, this is all great. Then why should you use COMPAS IFC for this? The thing is, direct interaction with IFC format is a huge pain in the ass. It is an enormous data schema of over 1,000 different classes interlinked with almost 3,000 relations, with terminologies, nomenclatures, and nuances even the most experienced developer can really struggle with a lot. And to give you a vivid example, to create the most basic legit IFC file like this, you need to write 500 lines of code using the pre-existing best tool called IFC OpenShell. While with COMPAS IFC, it was just going to be just like this. And to understand why it is so complicated and how did we simplify things so much, let's start with the most tricky part, the geometry. IFC supports a very wide range of geometry types, from very simple things like points, curves, to meshes, extrusions, solid models, all the way to very advanced representation types like a B-rep or freeform surfaces like NURBS. And while it can store all of this data for you, it provides no computational kernel to interpret them. This means that you have to handle everything by yourself, from simplest calculation like volume, surface areas, bounding boxes, to highly complex algorithms like a Boolean operation, clash detection, or translate them into your native CAD software and to visualize them. But with COMPAS ecosystem, many of these features can almost come for free. Through COMPAS IFC, you can directly use COMPAS geometry APIs to edit or create IFC files directly. And plus, different geometry types are automatically paired with state-of-the-art and battle-tested algorithms through libraries like COMPAS Sego or COMPAS OCC. You can visualize an IFC file with just one line of code through our integrated COMPAS viewer. You can also direct import, export advanced geometry types like B-reps or NURBS in between formats like IFC and STEP without worrying about data loss caused by a very common kind of thing like a tessellation. And the second important area is spatial relations, which defines how different building elements are organized in the project. And IFC defines its relational structure with a long list of classes, again, in highly detailed and implicit matter. Even, again, the most experienced developers can really struggle to navigate and understand it. And this makes it extremely fragile if you want to exchange just a part of the project, which is perhaps 99% of the case in real-world collaboration. And what you see here is a very common problem called exploding models, where elements snap into all random locations because those relations are broken during export. And through COMPAS IFC, we really try to clean up that mess. We use COMPAS model to organize all these relations into two clean and explicit structures. A spatial tree that handles all of the hierarchical relations, that tells you how everything is positioned, and an interaction graph that groups networking kind of relations like structural connections or MEP networks. And using these two structures to extract a certain scope of the project, say a building story here, becomes super easy with just a few lines of code. And in comparison, if you're going to do direct IFC manipulation, it would take you hundreds of lines and still give you all kinds of problems like misplaced objects or lost properties. And the last and also very important problem, especially for research, is that you are not really allowed to create custom classes in IFC. There's a workaround using what's called a proxy object and a custom property dataset. While indeed you can almost write any kind of data in any kind of form into those custom properties, but there is no official way to tell a third-party program that how to parse or process your custom data. And without that, whatever information you put there will just be silently dropped because the receiving end is not programmed in the same way like yours. And what we did is to allow users to define the built-in schema through Pydantic, the most widely used data modeling library in Python. And we automatically map that to the underlying IFC structure. And with this setup, you can easily define, share, and validate the custom building elements data either natively in Python or export them to JSON schema for other programming languages so that the receiving program has a clean and machine-readable instruction on how to treat your custom data. And there's a quick example here that's where we define the prefabricated concrete floor class with built-in schema for material, environmental, and structural properties. We loaded precise BREP geometries from step format, assembled the building model, automatically detected its structural connections, and exported a fully self-contained IFC file with zero information loss. And all of this is done under 200 lines of code. And to our knowledge, this level of integrated end-to-end workflow is almost unheard of in any existing tools. So on high level, what we try to achieve is a so-called front-end data model that serves as a simplified, intuitive layer for user interaction, while the full IFC file stays as the back-end, being this comprehensive single source of truth. And what this has achieved is a massive reduction from the full IFC complexity of over 4,000 classes and relations into just a 46 API endpoints that you as a user need to know about in order to work with this massive standard. So I hope by this point it's already convincing enough that COMPAS IFC can save you a huge amount of time. But if you are someone like me who almost does not code by hand anymore and just use an AI coding agent to do everything for you, the case here is actually even stronger that your AI should use COMPAS IFC as well. And in fact, what applies to humans works exactly the same for AI. Actually, it's what Tom just already said, exactly the same thing. So for humans, we should not keep reinventing the wheel. We should save our time by just using the battle-tested algorithm provided by COMPAS. For the AI agent, we should not encourage it to keep remake or hallucinate solutions. It should save its tokens and just take advantage of what's already existing. And that's why the most natural thing is to just package COMPAS IFC as well as the agent skill, and which you can easily install with one command, and so that not only you, but your coding agent like Claude Code or Codex can use it as well. And for next few short videos, I'm gonna just quickly show how I work these days. I almost don't, like I said, I don't program anymore. I just do my software engineering work through natural language. In fact, I'm not even typing, I'm just doing voice control. This is just asking, okay, if they have this skill installed. And once it's confirmed, we ask it to give me a quick summary of a model. Blah. How big is the file? What's the project name? Where is the location? And what does the building look like? And then I just say, yeah, can you just bring up the visualizer for me? Yeah, and we'll fire up the COMPAS viewer for that. See the next quick example. So yeah, I'm again voice controlling it, just saying that, asking it how many windows are there on the ground floor, ask it to do the query for me. And it's pretty fast, find out that there's 4 windows. Ask it to just show those 4 windows for me. And again, fire up the viewer with this isolated view of the 4 windows I'm asking about. A slightly more complex operation is that I want to, just see. So I wanted to ask it to export a Windows schedule for me with all of its metadata in Excel sheet. I mean, 2 minutes that I cut the video a little bit. It actually took about 1 minute because it does a lot of stuff. It inspects the elements, look at what data are available in each window, and look at the skill of how to write the Excel sheet. And it takes about 2 minutes, and it gives us this. And also there's another tab of summary, basically a bill of quantity of how many are there for each type of the window it finds. Last one. Rather advanced feature that a lot of Beam platform actually charge a lot of money for is a clutch detection. And again, with COMPAS IFC, it's just a matter of saying one line. Can you run clutch detection for this project for specifically structure and envelope element for me, and find out all of the collided pairs. And here is how it is visualized. Because this is our early concept model, right? There's actually a lot of clashes you can see. So yeah, this is about it. Thank you.